Okay, so in the last model, we had mu1 and mu2. It has two entries, and just call that list is mu1, and the second entry is mu2. Ditto with sigma. I'll create a little list that has two items long, sigma 1, sigma 2. And now, the new thing here for this model is that in the same way that I expressed that these are going to be normal distributions, but with a potential correlation between the two, we need to that new thing. They're special, bounded at -1 and 1. There's also, if we had many more sort of measures per person, we'd want a correlation matrix that's not a 2x2, but like a 3x3 or 4x4, and there's special constraints when you have that. So I actually have to use this special core matrix sort of initializer. Just like you've got a vector initializer to create a list of two items long, there's a core matrix initializer that creates a correlation matrix. When I say two here, it means that there's two things that I want to correlate. So it really is just going to have a single thing in that matrix that is the correlation between the two things. If it were more measures, it would have a correlation matrix with every pairwise correlation in it, but we won't deal with that yet.
The RHO is a correlation.
Sorry? Yep.
RHO is
Rho, yep. So that's a common Greek for correlations. It's not universal, but it's commonly used. So we've got a new parameter and slightly new sort of setup of the model, but it's hopefully should be a little bit familiar. What certainly is going to be new is the idea that we're actually sort of up in the, so far we've always had up in the data and parameters section, we've had this sort of initializer first and then the definition of a new variable. But we've never had that yet in the model section. This you don't really need to know much about. We're creating a new thing called Z. We're not calling it a parameter that we want to do inference on. Z is just a something that's going to reflect the combination of the variability and the correlation. Whenever you're talking about a multivariate normal distribution, you can say that, say it's a two-dimensional scatter plot. You could say that the dots on this axis have variability, or the dots have variability on this axis, and the dots have variability on this axis, and they have a correlation. You can combine those three pieces of information, the variability on the two axes plus the correlation, into something called a covariance matrix. And that's how most of the samplers for these things are expressed, not in terms of the variabilities and the correlation, but the covariance matrix. So in the same way that when you just talk about a normal distribution, you've got one parameter that specifies the center and one parameter that specifies the variability. And so far, all the things that we've used parameterize the variability in terms of the standard deviation. Why not the variance? Why not some other transform of the standard deviation? Just because we've chosen. In that same way, the multivariate normal, the functions that we're going to use to express that the data are distributed as multivariate normal, express it as the center of the multivariate normal, and then the second parameter is the covariance matrix. It would be more ideal if you actually just had the ability to say multinormal sigma rho. That would be more ideal, but they don't have that yet. So you have to create a new object called Z. It's not a parameter. It's just going to be sort of an intermediate variable that's used to be able to express that we're going to combine sigma and rho in order to say that the data come from a multivariate normal distribution. So you can actually see that we actually define what Z actually is just as sort of a combination of rho and sigma. You don't need to know what quad from diag actually is. It's a way of combining rho and sigma, just so Z is the covariance matrix that we need down here. What is down here? Well, it's saying that once we have the mu for each person and the Z for each, well, the mu, the mu's, the centers, and the covariance matrix express each person's data the row for each person, express that row as a sample from a multivariate normal distribution with this mean and this covariance matrix. So you have to loop over the data. That's what this 4-bit is. It's just saying that for each subject in our list of 1 through n subjects, express that person's row of data as deriving as a random sample from a multivariate normal distribution. It's the same idea as this, except the way this is structured, we didn't actually need to loop over people. We could just say all the people's observations are a sample. Here we have to actually, just because of the way the multivariate normal works, you have to actually express that you have to loop over each person. The last little bit that's new in this, so setting the priors on mu and sigma. Even though mu is a 2-item vector, in theory you could say mu1 is this one thing and mu2 is this other thing. But if they're going to be the same thing, we have the same prior for both variables because we've scaled them so that they should both have a center at about 100, or sorry, at 0. You can actually just omit specification of which one you're talking about, and it will apply the same prior to everything in that list. Ditto for sigma, it's going to apply this same log normal 0, 1 to everything in the list of sigma. Now this is new. Row, we have a prior on row. We know the correlations can go from -1 to 1. So why don't we just say we have a prior that's, say, maybe uniform from -1 to 1. That's because when we get to more complicated models that have more variables that could be correlated that we might be interested in, there's constraints on like what values the correlation matrix can actually take. So let's take the example of a scenario that's maybe related to your assignment, where you have 3 variables, A, B, and C. If you have a correlation of A and B of, say, 0.99, really strong relationship, and A and C of 0.99, really strong relationship, that constrains what B and C could have as a relationship. So you can't just sort of have a prior that's uniform and independent for each of these correlations. So there's just a trick to make it so that you have a uniform prior, but also it sort of constrains itself so it only talks about possible correlations. And LKJ, I think it's the first letter from the names of authors that came up with this way of creating this prior. It just means, so LKJ1 means that it's a uniform correlation matrix, and it will work for even more than 2 things that we're correlating. If you actually, this number on the inside expresses how, I guess, peaked your prior is at 0. So 1 means flat. If I put it at, say, 10, it would reflect I believe a 0 correlation very strongly for most of the correlations in this matrix. Probably don't want to do that. You probably want to sort of have a relatively uninformed prior about that correlation and let the data sort of drive what you eventually estimate.
So the higher the number, that means you more believe there's no correlation?
Yeah. So it expresses a stronger credibility in 0 and stronger disbelief in non-zero correlations. So it would be, if you actually had a sort of population with a correlation of 0.9, but you expressed a really strong belief, and you had a sample from that population, and you analyzed it using a very strong belief in 0, it would be harder to see that correlation. Your sort of final credible interval wouldn't be as influenced by the data as maybe you'd want it to. So a pretty standard uninformed or uninformative prior or weakly informative prior for the correlation is just to put a 1 there. You might notice that if you put a higher number, it might make more complicated models sample more quickly. But for the purposes of this really simple bivariate model, it samples very quickly anyway. So that's our model. We say that there's this sort of matrix of data coming in, these two columns. Each column has its own mean and its own variability, but they also have this potential correlation between the two columns.
What makes you choose a smaller versus a higher number?
It's in the same way that you want if you expressed a wide, let's say I put, we've standardized the data, but if I say 0.01, this would mean I'm very confident that the mean is somewhere very close to 0. But I probably don't want to do that. I probably want it to be a wider distribution. That's the same consequence as putting a 1 here means completely flat across the possible correlation matrices. I would equally believe any of those. So it reflects not a lot of confidence going in, and if you don't actually have a lot of prior data to base a confident belief on, that's a good value. All right, so it's a little bit more complicated in terms of how the model is expressed. We've got this new idea of sort of an intermediate variable that is being defined and combining other variables. The whole idea of a covariance matrix in the first place, and then the idea that you have to loop over subjects. But hopefully you can understand that all this is doing is taking in those two columns, saying that this column has a mean and standard deviation, this other column has a mean and standard deviation, and the two columns have a correlation. And it's trying to figure out what those means are, what those variabilities are, and what the correlation is. So going back to my model, my R code, I can use this to look at sample model 3 multivariate. I'm going to create the data, package the data up. So n is the same thing as always, the number of rows. Y now is going to be, it wants to be a matrix that is just the two columns. So cbind is a quick way to create that matrix. I'm combining together two columns. The first column, I'm going to give it, just like we had y1 equals this before, now I just put that as the first argument to cbind, and this as a second argument to cbind, and that creates a matrix with two columns, and each column has been scaled.
So if you have 3 columns, you just split that to...
Yep. If you had a third variable, you'd add it in here. So that creates a data, and we'll sample, and it should sample fairly quickly. Now you can actually see the progress indicator going. This reflects that we've got a more complicated model than we used to have. And we get out a little table of results. The means should actually be pretty similar to what they used to be in the previous examples where we did either the difference score all by itself, or the version where we had the difference score and the intercept in the same model, but not really expressing any relationship between those two properties. Now we actually do have the relationship between the two properties, and that's expressed in this row bit. But this row bit is actually a little bit hard to read. It's because in theory, there's just one correlation that we're interested in between these two variables. But by setting it up as a correlation matrix, it has created a correlation matrix. And if you remember correlation matrices, usually, let me actually just try it out. We have I guess the intercept and effect, So the correlation we're actually interested in is right here, rho. So that is the correlation between I and delta. This This is also I and delta. So this is also that same value, rho. The diagonal is always going to be 1 in the correlation matrix. So if we actually look at this table, you'll see the matrix subsetting syntax that R uses, such as square brackets, the thing before, and then comma. The thing before the comma is the row it's referring to. The thing after the comma is the column it's referring to. So 1, 1 is this upper diagonal, and 2, 2 is the lower diagonal. And if we see 1, 1, and 2, 2, they're both just filled with 1. 1, 2 is this off diagonal here, and 2, 1 is this other diagonal, and they're the same thing. So really, you can look at either row 1, 2 or row 2, 1. It's the same thing. So what this is reflecting is the credible interval on that correlation between the intercept and the effect.
What's the NA term?
That happens sometimes. It shouldn't, I mean, frankly, it shouldn't actually be including those two sort of cells of the correlation matrix in this at all, just like it shouldn't have the redundant cells. I've asked them to fix that so we get prettier output. But yeah, you can ignore that. I told you the previous rule is make sure that it's all 1 in this R hat column and all above 1,000 in this NF column. If you get an NaN, but it's for sort of a cell in the correlation matrix that is supposed to be just all 1, that makes it, for some reason, break for this first entry, but the other one, so 2, 2, doesn't break. No idea why. So we could go through and figure out what should we believe about the difference score after rescaling it, and what should we believe about the intercept after rescale it, their locations. But we've already done that, so you can use the code that we had before. But the critical thing that's new in this model is that we can talk about what should we believe about the relationship between the intercept and the effect. Here I happen to create some data where I actually didn't have any true correlation generating the data. I should have created a more interesting scenario. So our credible interval after the fact ranges from negative 0.33 to positive 0.03. And this, remember, is the correlation scale that's bounded at negative 1 and 1. So 0 is within that 95% credible interval. So 0 remains a credible value for the true population correlation. So I wouldn't try to assert that there's a nice strong correlation or anything like that in the data.
Do you need to have scaled the data to get correlation?
No. If I hadn't scaled the data, and if I don't scale the data, that means that you have to put you have to decide what priors you want on the mu and sigma, but rho's prior and what rho's value is completely independent of those two things. It's always on that scale of negative 1 to 1 in terms of what it spits out as its output, and you probably just always want to use this LKJ core 1 as the prior for a correlation parameter. So that's actually all I wanted to do today. So I could say there are scenarios where you do get consistent. You would get a scenario where somebody, for example, with high overall scores would have a greater sort of response or difference between the 2 time points. This also generalizes to more than just 2 time points. If you had a 3rd time point, we'll maybe get into that after we deal with a couple other types of scenarios. Yeah, this general idea, I think growth modeling I've seen is more prevalent as a term in the medical communities, particularly for this idea of having the ability to speak to the correlation between the parameters, and also particularly in the context where you have multiple time points, more than just 2. Yeah, got a question over here?
Yeah, how can you say that they're not actually like related to each other?
Well, Yeah, so I'm looking at this entry in the correlation matrix, the only off diagonal entry, and that's expressing the credible interval for the correlation between intercept and effect, and that credible interval includes 0. And so I would be hard pressed to say that 0 is a not very credible value, and indeed I would say it's still relatively credible. Yeah. All right. So short class today. The assignment is due Friday at 11:59, and next week, or I guess Thursday, we'll talk about an extension of this type of model to a scenario. So if you go look through the lecture that I sent you last week, it's a lot of this stuff plus a little bit at the end that will address what you guys have to do for your assignment for Friday. I didn't want to do it in class today, lest I give away the answers. So. Yeah, so I guess no tutorial next week. Yep.
Next week is reading week, isn't it?
Yeah, there's no class either.
No?
No. Yeah.
Oh my god, you scared Mary.
And here.